So we can do chemical reactions in the lab and we can measure the amount of heat that's absorbed or given off by a chemical reaction. And we use a little device called a calorimeter. And a calorimeter is basically a styrofoam cup, and you use two of them, and then you have a styrofoam lid on top. Usually water is put in or some sort of solution, and then a thermometer is inserted through the lid. You want to keep everything all nice and tight to keep all the heat in your little calorimeter cup. So what happens again is the reaction will occur in the water and the heat from the reaction will transfer to the water, and then I can measure the temperature of the water to figure out how much heat the reaction gave off. Or perhaps the reaction is absorbing heat and it will get that from the water. The water will supply that energy. So we can use this little container and then use a calculation to determine the amount of energy gained or lost during a chemical reaction. And this coffee cup calorimeter, or the styrofoam cup calorimeter, it is only used for solids and liquids and mostly solutions. We're dissolving things and seeing if they absorb or give off heat. If you had a gas, you wouldn't be able to use this system because the gas would obviously leak out because it's not airtight. So for gases, you would use something called a bomb calorimeter. So you have a little container surrounded by water that will be airtight. You can put your gases in there, and then you'll have a triggering device, a sparking device that can spark it and provide that activation energy to get it going. So in the perhaps combustion reaction that is in here, where you are reacting two gases together, what will absorb that heat from those gases reacting is the jacket of water that surrounds it. So it's still set up just like the other calorimeter, only we just have an airtight container that is found in the bomb calorimeter. And I do not have one of these in the lab to show you, so this is more like you would do bomb calorimetry in a college lab. Now for calorimetry, you need to know the initial temperature, the final temperature, and the mass of the water. You do not need to know how fast the temperature changes, but just the beginning temperature and the ending temperature. And we're going to be using this formula that we've used before. Q equals mc delta T. So Q is the energy. So remember, this is a laboratory delta H, or the heat content, or it's also called the enthalpy. M is the mass of the sample in grams. C is the specific heat, and you will always be given what the specific heat is. If you're not given what it is, then we are going to use the specific heat for water. And the specific heat for water is 4.18. And it has a whole bunch of units that are attached to it that help you cancel your units. We've looked at heating and cooling curves. This is a heating curve, where you take and you heat up your solid, and then you melt your solid, and then you heat up your water, and then you boil your water, and then heat your steam. And we're only using this area of that heating curve where you're heating the water. So we're going to use the specific heat for water. So that's why it's 4.18. Now, when you look at your reaction that's giving off the heat and your water or your solution that's gaining the heat, they will be equal in value. So but they will be opposite in sign, because one is going to have the heat leaving, so it will have a negative number, and one is going to be absorbing that heat, so it'll be a positive number. Overall, your heat is not going to change. So this is observing that conservation of energy. Again, the water will absorb or give energy to the reaction or absorb it from the reaction. The sign tells the direction. You really can't have a negative quantity of heat. If there is a negative sign, it's just showing you that it's leaving. So in an exothermic reaction, and you do need to know these, the reaction is going to give off heat. And so notice the sign is a negative, and the water or that solution is going to gain that heat. So they'll be equal in values, but just opposite in charge. And so the surroundings to us will feel warm. So exothermic reactions, the temperature will go up. And then in endothermic, it's the opposite. So the reaction is going to pull in heat from the water or the surroundings. And so my water is going to have a negative sign and my reaction will have a positive sign. So the only thing we can measure is the solution. I can't measure the reaction. So whatever I measure in the water, the reaction has the same number value, but it's just the opposite in charge. So in class, I did a little demonstration. So I measured 11.2 grams of sodium hydroxide. So this is a base, it's also a salt, and I put it into 75 grams of water. So I really measured 75 milliliters, but 1 milliliter is equal to 1 gram, and so it's just a really easy conversion. And we measured what the temperature changed. Then the temperature changed from 22.2 to 58.5. What type of chemical reaction is this? Is it exothermic or endothermic? And because the temperature goes up, this will be exothermic. So my reaction is giving off the heat, my water is absorbing it. So we can only measure the water, and so we measure that the temperature goes up. We are going to use the formula Q equals mc delta T. To find the delta T, you are going to take the final temperature and subtract the initial temperature, or that beginning temperature. So let's go ahead and do this. So we have 58.5 and subtract 22.2, and I get 36.3 degrees Celsius. That is my change in temperature. My mass is found by taking and adding the solute and the solvent. My solute is 11.2 grams, and my solvent is 75 grams. So my total mass is going to be 86.2 grams. And the specific heat is not given, but we are going to use the specific heat of water, and so that's going to be 4.18. So you should always be told that, but if I forget to tell you in the problem, then you're just going to use the one for water. And it's going to be pretty close. It is not pure water, but it's a solution because we're going to dissolve this salt into the water. But it's going to be really close, like 4.2. So not a lot of error for just using the water specific heat. So let's go ahead and plug it into our formula. So again, my Q is equal to the mass, so 86.2 grams, times the specific heat. And it has all those units so that our units will cancel and we'll be left with joules. And I have 36.3 degrees Celsius. So when I multiply this out, I get 13,080 joules. So remember, joules are really, really small. So that's why this number is so big. And our temperature went up a lot. So there's really a lot of energy found in that 11.2 grams. So as it dissolved and the bonds were broken between the sodium and the hydroxide, it released all this energy. So now what I found here was my solution, or it's my water. Okay, I'm just going to put SOL, so that's my solution. This next question, it's asking about the reaction. When you look at the reaction compared to the solution, remember the solution is your surroundings. So now I want to look at what's happening in the reaction. So remember, the solution and the reaction, they will have the exact same value, but just opposite sign. So my reaction gave up this heat. So equal in quantity, but opposite in the sign or in the charge. So this is showing that I have 13,080 joules leave the reaction. Where did that heat go? It went into the water or the solution so that I could then measure that to determine how much heat left. All right, now in this part B, we need to calculate the enthalpy of solution, and then here's our formula, kilojoules per mole. So I want to find the kilojoules, and then I want to find the moles, and I'm going to just put them on top of each other and divide. So I already know what my joules are, so to go from joules to kilojoules, I'm going to divide by 1,000 or move your decimal over 3. So 1,000 kilojoules in 1,000 joules in 1 kilojoule. And so I'm going to get 13.08 kilojoules. So I can just go ahead and put that into my formula right now. And don't forget the negative sign. So 13.08 kilojoules. Because this is exothermic, the energy is leaving my reaction and going into my water. That's why my water got all hot. Now I need to figure out how many moles we have. Now this is moles of the chemical. So I am not looking at the water. I'm looking at the reaction. And in my reaction, I have 11.2 grams of the sodium hydroxide. So I need to figure out how many moles that is. So I'm going to add up 1 sodium. So this is like 23, and this is 16, and this is 1. And I'm going to get 40 grams in 1 mole. So when I divide that out, I get a small number. So this isn't a very big number. So 0.28 moles. And then I'm just going to stick it right here. So I have 0.28 moles. And dividing out, I get 13.8 divided by 0.28. I get a negative 46.7. So I have a negative 46.7 kilojoules of heat that is released if I were to put 1 mole in that calorimeter. So I didn't put 40 grams in the calorimeter. I only put 11.2 grams. So this is a way to calculate the small amount that you dissolved, what it would be if you had a larger amount. So again, we use the surroundings to help us determine what's going on in the reaction, and then we're able to determine how many kilojoules per mole is produced. And we know it's exothermic. Why? Because it's a negative sign. That means that this energy is leaving the reaction and going into the water. Another type of calorimetry problem you might see is a lot simpler than the one that we just did. So the one that we just did is about as hard as I'm going to give you a problem to do. This one is more straightforward. So I am going to still use the formula Q equals MC delta T, and I'm going to be given everything but one of the values. So let's go ahead and figure out which one thing do we need to find. So this says calculate the specific heat of platinum. So I need to find the C. So this is what I'm going to solve. I have my Q, it's right here. There's my joules. I have my mass right here, they tell me. And then this is my delta T. So I don't have to take final minus initial. It just tells me the total amount that it changed. You can plug all these values directly right into your Q equals MC delta T formula, or I'm just going to rearrange it. So I want to get C all by itself, so I'm going to divide by the mass and the temperature on both sides. So on this side, it will all cancel out, so I'll have specific heat equals Q divided by the mass times the delta T. Now, if that makes your brain hurt, go ahead and not do that step. Just plug it directly into the Q equals MC delta T formula and solve for C, making sure you pay attention to all your algebra rules. So I know what my Q is. It's 1,092 joules, and my mass is 125 grams, and my delta T is 65.2 degrees Celsius. My units are going to not cancel out, so specific heat has all of these units. And I'll go ahead and plug this into my calculator. And I get a very small specific heat. This is a lot smaller than water. So your metals tend to be a lower specific heat. And that is because they're such good conductors. They don't really absorb a lot of energy. So they just kind of grab it and move it on. All right, so here's more of a simple problem using the Q equals MC delta T formula. So another enthalpy or energy problem that you might see is using a balanced chemical reaction to help you figure out how much energy is going to be produced if you have a certain starting amount. So looking at this balanced chemical reaction, this is a reaction that is used to power the blast off of the space shuttle. So basically, we take hydrogen and oxygen gas and combine it to form water vapor. And this is very exothermic. It releases a lot of energy and not harmful for the environment. And so this is what's used. We get a lot of power from this reaction. Another enthalpy or energy problem that you might see is using a balanced chemical reaction. So in this balanced chemical reaction, I have 2 moles of this hydrogen, and it will produce my 483.6 kilojoules of heat that is released. Or I could look at the oxygen. 1 mole of this as a reactant produces the same amount. Or I could have 2 moles of this product would produce the same amount. So we can use our balanced chemical reaction as a conversion factor. So I can convert from moles to energy. So looking at this problem, and by the way, this is the reaction that powered the space shuttle. So let's look at this problem. What is the enthalpy change when 178 grams of water are produced? So the number we start with is 178 grams. And looking at my balanced reaction, everything's in moles. So that's my first conversion I'm going to do. I'm going to convert from grams to moles. So there are 18 grams of water in 1 mole of water. And I got that 18 by adding it up. So there's 2 1 gram amount, and then oxygen is 16 grams. So adding that up, I get 18 grams. All right, so I'm in moles of water. So looking at my balanced reaction, 2 moles of water gives me this much energy. So I'm going to put 2 moles of water down here, and I have a negative 483.6 kilojoules up here. So 175 grams is a lot of moles because there's only 18 grams in 1 mole. So this should be a pretty large number. So let's go ahead and look and see what it is. So 175 grams times 1 divided by 18 times 483.6. So I get a negative 4,780 kilojoules. So 178 grams will give me this amount of energy. And I just get it by looking at the molar ratios in the balanced equation.